There is a star in our sky that you have almost certainly never seen, even though it is the closest one there is. It sits low in the far southern sky, below the horizon for most of the northern half of the world, hiding in plain sight beside two of the brightest stars we have. And here is the strange part. Even if you stood beneath it tonight, under the clearest, darkest desert sky on Earth, you still would not see it. Not because it hides, because it is small and cool and faint, a star built on very nearly the minimum a star is allowed to be. Its name is Proxima, Proxima Centauri, the nearest star to the Sun. It is a little over 4 light-years away, next door by the standards of a galaxy 100,000 light-years wide, unreachable by the standards of everything human beings have ever built. Tonight, I want to walk that road with you, slowly, the way we do things here. I want to show you what is actually there, at the nearest star, because it is stranger and more crowded than most people imagine. I want to show you the worlds we found circling it, and we did find worlds. That part is no longer speculation. I want to look honestly at the road itself, how a thing made by human hands might ever cross that gap, what it would cost, and what it would do to anyone who tried to ride along. And I want to be truthful with you about where the facts end and where the dreaming begins, because this story has plenty of both. It is a long story. You do not need to stay awake for it. That is rather the point. So get comfortable. Let the lights go. We are going to visit the nearest star. Start with the distance, because everything else in this story bends around it. 4¼ light-years. The number slides past you like water. Light-years always sound like poetry instead of measurement. So let me make it physical. Shrink the sun down to the size of a grapefruit, 14 centimeters across, something you could hold in one hand. On that scale, the Earth is a grain of sand about 15 meters away. Walk 15 steps from the fruit, and you have crossed the orbit of our entire world. Neptune, the outermost planet, becomes a small seed circling nearly half a kilometer out. The whole solar system, every planet, every probe, every place a human machine has ever touched, fits inside a few quiet city blocks. Now ask where the next grapefruit sits, the nearest star to ours. The answer is 4,000 kilometers away. One piece of fruit resting in a city square, and the next one on the far side of a continent. That is what the word nearest means out here. And the space between them is not full of anything. No fog, no wall, no river to cross. A few drifting atoms in every handful of emptiness. Some ice, some dust. The occasional wandering comet sleeping between the streetlights. The gap is not the obstacle on the road. The gap is the road. The farthest machines we have ever thrown into that emptiness are the 2 Voyager probes. I told their whole story here recently, and if you slept through some of it, they will not mind. Voyager 1 is leaving the solar system at about 17 kilometers every second. That is fast enough to cross the Atlantic Ocean in around 6 minutes. It is not aimed at the nearest star. But if it were, if that speed were pointed straight down the road we are walking tonight, the trip would take roughly 75,000 years. 75,000 years ago, there were still Neanderthals in Europe. Launch to arrival, 1 trip, nearest star. That is the scale of the problem. Hold it gently. We will come back to it. And yet, light crosses that same gap in 4 years and 3 months. The starlight arriving from that southern sky tonight left home while you were living an earlier version of your own life. Whatever you were doing 4 years ago, that is when this light began its trip. By the standards of the universe, that is not far. That is intimate. That is a letter from someone in the next valley. Which brings us to the address itself. Because here is the first thing most people never learn about the nearest star. It is not 1 star, it is 3. 2 of them travel together as a pair, Alpha Centauri A and Alpha Centauri B, circling one another in a slow orbit that takes about 80 years to complete. Alpha Centauri A is a star like our Sun, the same class, the same warm white light, a little heavier, a little brighter. If some cosmic hand swapped it for ours, the daylight would feel almost familiar. Alpha Centauri B is smaller and orange, a cooler star, thriftier with its fuel, the kind of star that plans to be around for a very long time. As they orbit, the distance between them breathes. At their closest, they sit about as far apart as the Sun and Saturn. At their widest, more like the Sun and Pluto. Closing and opening every 80 years, for billions of years. Seen from Earth, the pair blends into a single brilliant point, the third brightest star in the entire night sky. Sailors steered by it for centuries. Whole navigation traditions leaned on that point of light, without anyone suspecting it was two suns pretending to be one. And then, far out beyond the bright pair, there is the third one, the quiet one, Proxima, a red dwarf, carrying only about an eighth of the sun's mass, close to the least a ball of gas can weigh, and still ignite as a true star. Its surface smolders at around half the temperature of the sun's, glowing the color of embers rather than daylight. And it is small in a way that is hard to believe. Proxima is only about 1.5 times as wide as Jupiter, a star, genuinely fusing hydrogen, barely wider than a planet we can see with the naked eye. But do not let the size fool you. It holds roughly 130 times Jupiter's mass, squeezed into that modest frame. Squeezed that tight, it burns with extraordinary patience. Red dwarfs like Proxima are the misers of the galaxy. They spend their fuel so slowly that they will still be shining, much as they do now, trillions of years from today. Hundreds of times longer than our sun will last. The frugal little star next door will quietly outlive every bright thing you can find in tonight's sky. Proxima belongs to the bright pair, but loosely, it circles them at an enormous distance, taking something like 500,000 years to complete a single orbit. It sits so far from its companions that, seen from Proxima, they would not look like suns at all. Just two dazzling stars in the night, bright enough to cast faint shadows, but stars nonetheless. 3 suns, then. 1 bound family, 1 address, 4.25 light years from your window. Here is something I find quietly moving. We have only known the nearest star existed for about a century. In 1915, an astronomer named Robert Innes, working at an observatory in South Africa, noticed a faint red point of light that moved across the sky in step with the bright Centauri pair. Same direction, same pace. A companion, tagging along. When the measurements were done, the faint red point turned out to be closer to us than the bright pair itself. Innes proposed the name Proxima, the nearest. 100 years on, the name still holds. Every survey since, every satellite census of the sun's neighborhood, nothing has ever been found closer. Though I should say, in the spirit of honesty this channel runs on, the title is not permanent. The stars are all moving. The whole neighborhood is slow traffic, drifting on orbits around the galaxy, and the map redraws itself over tens of thousands of years. The Centauri system is actually approaching us. In about 28,000 years it will pass at its closest, noticeably nearer than it is today, before beginning the long drift away again. The road we are studying tonight is slowly getting shorter, all by itself. Not by much, but I like knowing that. For most of the century we knew about these 3 suns. That was the entire story. 3 stars, various distances, nothing more to say. Planets? Nobody knew. Nobody could know. The instruments were nowhere near good enough. A planet beside a star is a firefly beside a lighthouse, seen from another continent. Textbooks simply left the question open, the way you leave a room unlit when you have no way to reach the switch. Then in the summer of 2016, at a European observatory high in the Chilean desert, a small team of astronomers finished checking and rechecking a signal they had been quietly chasing for years. A tiny, rhythmic sway in Proxima's light. A pull, and release. Something small was tugging on the nearest star, gently, patiently, once every 11 days. There is only one thing that does that. A planet, at least as heavy as the Earth, circling the nearest star once every 11 days in the one narrow band around that dim ember where water, liquid water, could survive on a surface. The nearest star has a world. Let that settle for a moment, because it is easy to say and enormous to mean. The very first star beyond our sun, the closest porchlight in the whole galaxy, and there is a planet there, in the temperate zone. When that announcement came, the road we are walking tonight changed its nature. Because before 2016, a journey to Alpha Centauri was a journey to 3 points of light. Now, it is a journey to a place. A road only really becomes a road when it leads somewhere. We will meet that world properly soon, how it was caught, what it might be like to stand there under a red sun, and the 2 other worlds found in the same system since. We will also meet a newer mystery, a faint something the James Webb telescope may have glimpsed beside the sun-like star next door, seen once, then lost, and still not confirmed. The nearest system is keeping secrets from us in real time. And then, once we know what is waiting there, we will turn to the question underneath this whole night: how anything built by human hands could ever make the crossing. But that is all still ahead, and there is no hurry. The stars certainly are not in one. For now, just hold the picture. A grapefruit in a city square, a grain of sand 15 steps away, and 4,000 kilometers of quiet darkness before the next fruit, where 3 suns and at least 1 world are waiting for a visitor. The road is long. We have all night. And the first steps, at least, we have already taken, with our eyes. Before we walk the road, let us look properly at where it leads. Because the discovery of that first world, the planet around Proxima, is one of the quietest, great detective stories in modern science. Here is the problem the detectives faced. You cannot see a planet around another star. Not directly, not usually. A star shines with its own light. A planet only borrows a little of it. Beside even a dim star like Proxima, a planet is a dust mote drifting next to a lit candle, and the candle is 4 light-years away. So astronomers stopped trying to see planets and started trying to feel them. A planet does not simply circle its star. The truth is more delicate. The star and the planet circle each other around their common center of balance. The star is thousands of times heavier, so its share of the dance is tiny, a slow, patient sway, back and forth, a few meters per second. Walking pace. Think about that. A star, a ball of burning gas hundreds of thousands of kilometers across, swaying at the speed of a person strolling through a park, because something small keeps tugging its sleeve. And we can measure that. From 4 light-years away, through a telescope, we can catch a star breathing in and out at walking pace. The trick is color. When the star sways toward us, its light shifts a whisper bluer. When it sways away, a whisper redder. The same effect that bends the pitch of a passing siren, applied to starlight. Measure the shift, night after night, year after year, and if the sway repeats, steadily, on schedule, like a metronome, then something with mass is orbiting that star, and you can even weigh it. That is the method. And I want you to appreciate for a moment the machine that makes it possible. Because the instrument at the heart of this story is one of the quiet masterpieces of our age. It is called a spectrograph. It takes starlight and combs it apart into its colors, finely enough to notice a shift of 1 part in 100 million. To hold that precision, the instrument lives sealed in a vacuum tank, in a cellar beneath the telescope, its temperature guarded to within 1,000th of a degree for years on end, because a draft, a footstep, a warm afternoon would smear the measurement into nonsense. Astronomers walk softly around it, the way you would around a sleeping animal. A machine that can feel a star breathing must not be allowed to feel anything else. And by the 2000s, instruments of this family had already rewritten astronomy once. They had found hundreds of worlds around other suns, hot giants and strange super-Earths, a whole zoo nobody predicted. I told part of that story in an earlier night here, about how far we can go. The short version is that by the time our story begins, planet hunting had become a craft, with tools, veterans, and rivalries. What it had not yet done was answer the question everyone asked first and always. Fine, but is there anything around the nearest one? Now the story. By the early 2010s, there were hints. Proxima's light seemed to carry a faint rhythm, buried under noise, a maybe, a shadow of a signal, nothing anyone could defend. And red dwarfs are deceptive witnesses. They are restless little stars, spotted and flaring, and their own weather can fake exactly the kind of signal a planet would make. Many claimed planets around red dwarfs have dissolved, on closer inspection, into star spots. So in January 2016, a team led by an astronomer named Guillaume Anglada Escudé decided to settle it, in the most direct way imaginable. Watch the star every single night, and in public. They called the campaign Pale Red Dot. A tip of the hat to Carl Sagan's Pale Blue Dot, but for a world that, if it existed, would circle a red sun. For about 3 months, from January into the spring of 2016, a telescope in the Chilean desert, at the La Silla Observatory, high and dry on the edge of the Atacama, measured Proxima's sway. Night after night. One star, 60 nights of data. I find something lovely in the openness of it. They announced in advance what they were doing. They published updates as they went. Whatever the answer turned out to be, planet or no planet, the search itself was going to be honest. And the metronome was there. Once every 11.2 days, Proxima Centauri leans toward us, and then away, at about walking pace, and it has been doing so the entire time we have known how to look. There is a version of this story where the campaign ends in embarrassment, where the rhythm dissolves into star spots like so many before it, and Pale Red Dot becomes a cautionary tale about doing science in public. The team knew it. They ran every test they could invent. Does the signal match the star's rotation? Does it wander the way stellar weather wanders? Does it appear in one instrument and not another? It passed everything. The 11-day sway had been hiding in older data all along, they found. 16 years of archived measurements, whispering the same period, waiting for someone to listen hard enough. In August 2016, the team published the result, Proxima b, a planet at least 1 3/10 the mass of the Earth, give or take. The number is a minimum, because this method weighs a planet slightly blind, but everything says it is a small, likely rocky world. Let me unpack that phrase, slightly blind, because it is a lovely piece of honesty baked into the physics. The sway tells you how hard the planet pulls along our line of sight. But if its orbit is tilted toward us, part of the pull hides in a direction we cannot measure. So the method reports a floor, not a weight. This heavy, at least. For Proxima b, the floor is just above 1 Earth. The ceiling, statistically, is not far higher. A small world, almost certainly. But science writes down what it knows, and footnotes what it hopes. The announcement went out on a Wednesday evening, European time, and by morning the nearest star had planets in 100 languages. I remember the maps the newspapers printed, the little diagram, our sun and its neighbor, with a green band drawn around the red dot, and a world sitting neatly inside it. And here is the part that made the whole field sit up. Proxima is dim. It pours out only a small fraction of the sun's warmth, so its zone of comfort, the band of distances where water on a surface could stay liquid, hugs the star closely. Proxima b orbits at about 1/20th of the distance from the Earth to the Sun, 7.5 million kilometers. It circles its entire year in 11 days. Around our Sun, that orbit would be an oven. Around a cool red ember, It is precisely the temperate band. The nearest star beyond the Sun has a roughly Earth-sized world, in the habitable zone. Not a special star far away, the next one over. When people say the galaxy is probably full of worlds, this is the evidence they are leaning on, whether they know it or not. We looked at the very nearest star, one single star, chosen not because it was promising, but because it was close, and there was a temperate world waiting. Either we were absurdly lucky, or planets like this are everywhere. Let that thought loosen your shoulders a little. Either answer is wonderful, and Proxima was not finished with us. The same instruments kept listening in the years that followed, newer ones too, sharper ones, on the giant telescopes at Paranal, further north in the same desert. In 2020, buried in the data, a second, fainter metronome appeared. Much quicker, much gentler. Confirmed properly in 2022. Proxima d, a little world skimming the star once every 5 days, closer in than the temperate band, a warm, small thing, probably only a quarter of the Earth's mass. One of the lightest planets ever weighed by the sway of its star. And further out, there is a third rhythm, a slow one, a candidate called Proxima c, a heavier world, several Earth masses, taking about 5 years to circle round, far outside the zone of warmth, out where any water would be iron-hard ice. I will be honest with you, in the way this channel tries to be. Proxima c is not certain. The signal is long and faint, the star is temperamental, and some careful people remain unconvinced. Hold it gently, as a probably rather than a fact. But step back and look at what the picture has become. The nearest star is not a lonely ember after all. It is a small planetary system. An inner world hurrying round in 5 days, a temperate world in 11, perhaps a cold outer sibling on a 5-year road. A family of worlds, arranged around the smallest kind of star there is, 4¼ light years from where you are lying right now. And red dwarfs, it turns out, are exactly where you should expect to find such families. They are the most common kind of star in the entire galaxy. Roughly 3 of every 4 stars that exist is a small red ember like Proxima. The bright suns like ours, the ones that fill our storybooks, are actually the minority. The typical star in the Milky Way is dim, red, frugal, and long-lived, and, on the evidence gathering year by year, very often accompanied by small, rocky worlds. Put those 2 facts together and something quietly staggering falls out. If the commonest star routinely carries rocky planets, and if even a fraction of those sit in the temperate zone, then the galaxy is not sprinkled with a few precious Earth-like worlds. It is paved with them, billions upon billions, most of them circling red embers under skies the color of a permanent sunset. We did not have to travel to learn this. We learned it by looking hardest at the single nearest example and finding it already occupied. The nearest star was not special. It was representative. That is the more unsettling reading, and the more likely one. It is worth pausing on how young all of this is. The very first planet confirmed around an ordinary sun-like star was found in 1995. A hot giant hugging a star called 51 Pegasi, a world so close to its sun that its year lasts 4 days. That discovery won a Nobel Prize, and it is younger than a great many people listening to me now. Before 1995, the honest scientific position on planets around other stars was, we assume they exist, but we have never seen one, and we may never be able to. Within 30 years, we went from 0 to a handful to hundreds to thousands. The count of confirmed worlds beyond our sun now runs well past 5,000 and climbs every month. And in that same span, the story sharpened from any planets at all to a temperate world around the very nearest star. That is not a slow science creeping forward. That is a door blown off its hinges inside a single generation. I try to remember that, on the nights when the world feels stuck and old. Somewhere in the ordinary run of one human lifetime, our species quietly learned that the sky is full of worlds, and that the closest one has a neighbor waiting in the temperate zone. We happen to be the people who were alive when that stopped being a guess. When I was a child, every book said the same thing. We know of 9 planets, all of them here, and nobody knows if any other star has planets at all. That sentence died within my lifetime. Quietly, one measurement at a time, and it died first, fittingly, at the star next door. So the address is real, and the address is inhabited by worlds, whatever else may or may not live there. The next question asks itself, could anything live there? Is Proxima b actually a place, with weather and mornings and seas, or just a mass on a chart? That question turns out to be one of the most interesting arguments in modern astronomy. A red sun changes everything: the sky, the seasons, the very idea of a day. And there is a complication. Proxima, the gentle ember, has a temper. That story is next. Stay comfortable. The worlds will still be there in the morning. So there is a world in the temperate zone of the nearest star. Now comes the harder, more human question. What is it like to stand there? Start with the sun in its sky, because nothing else about Proxima b makes sense until you feel how strange its star would look. Proxima b orbits 20 times closer to its star than we do to ours. So even though Proxima is a dim little ember, it hangs in that planet's sky enormous, roughly 3 times the width of our sun as seen from Earth. A vast, quiet, coal-red lamp, taking up a thumb's width of sky at arm's length. Its light is not like ours. Proxima shines mostly in deep red and infrared, warmth more than brightness. Noon on Proxima b, at its brightest, might feel to human eyes like the last few minutes of a heavy sunset. Forever. Plants, if such a world grew any, would face an interesting problem. Red light is what most photosynthesis on Earth already harvests, so the machinery could work, but some researchers suspect vegetation under a red dwarf would grow dark, nearly black, to swallow every photon it can. Black meadows under a red sun. That is speculation, clearly labeled, but it is honest speculation. Now the day itself, or rather, the lack of one. A planet that close to its star lives inside a powerful tide. The star's gravity needs it, breaks it, and over billions of years almost certainly forces its spin into lockstep, the same face turned starward forever, the way the moon shows one face to the Earth. If Proxima b is locked like that, then it has no days at all. One hemisphere lives in permanent afternoon, the other in permanent starlit night. And between them runs a ring of eternal evening, a terminator, a band of dusk that never moves, circling the planet like a seam. Imagine having an address there. Not a time of day, a place of day. You could walk from noon toward midnight and stop halfway, where the red sun sits on the horizon and never leaves it. I have thought about that band of permanent sunset more often than I should probably admit. There is a gentler possibility. Some orbits settle into a rhythm like Mercury's, turning 3 times for every 2 laps, which would give the planet slow, strange days. But locked or not, the clock of that world is nothing like ours. Astronomers have a wonderfully unofficial name for the locked kind of world: an eyeball planet. Seen from space, the models say, it could genuinely look like one: a warm, possibly liquid center on the day side, an iris of milder ground around it, and the white of frozen night wrapping the rest. A planet-sized eye, gazing at its star forever, unable to blink. And the seasons? There are none in our sense. No spring, because nothing tilts and swings the light. What Proxima b has instead is a faint pulse. Its orbit is slightly oval, so the giant red sun swells and shrinks a little in the sky, week on week, the whole world's warmth breathing gently on an 11-day cycle forever. If it has oceans, they have tides of light instead of seasons. One more texture for the night side, since we will never stop imagining it. If the planet holds an atmosphere and a magnetic field, then its dark hemisphere is not entirely dark. Every flare from the little star would pour particles down the field lines, and the permanent night would answer with aurorae, sheets of silent color over black ice, feeding on the same storms we are about to accuse of murder. The universe rarely builds a threat without building something beautiful out of the same parts. Climate models say a locked world is not doomed, by the way. This surprised people. An atmosphere, if there is one, becomes a courier. Winds carrying heat from the day face to the night face, evening out the extremes. With enough air or ocean, the night side need not freeze solid. Some models even paint the day side with a single vast, calm ocean under that red glare. But all of those pictures rest on one enormous if. If there is an atmosphere. And here we meet the temper of the little star. Proxima looks placid. It is not. Small red dwarfs are convective all the way through. They churn, top to bottom, like water simmering, and that churning winds up magnetic fields that snap and reconnect violently. When they snap, the star flares. In March 2016, while the Pale Red Dot campaign was quietly listening as it happens, Proxima produced a superflare. For a few minutes, this dim ember, invisible to the naked eye, brightened dozens of times over. Had you been watching that patch of southern sky, the nearest star would have flickered up toward the edge of naked eye visibility. Briefly, like a signal lamp. Later, radio telescopes caught another outburst, a flare that brightened the star 1,000-fold at some wavelengths, in seconds. For the planet, sitting 20 times closer than we sit to our sun, each of those events is a storm of ultraviolet and X-ray light washing over the sky. Averaged over time, Proxima b likely receives hundreds of times more X-ray radiation than the Earth does. And beyond the light, there is the wind, the stream of charged particles a star constantly exhales, which for a close-in planet blows far harder than anything the Earth endures. That is the case for the prosecution. A steady sand blasting that, given a few billion years, might strip a planet's atmosphere away entirely, molecule by molecule, and leave the temperate world airless, technically in the habitable zone, and dead as our moon. Mars, in our own backyard, lost most of its air to a far gentler wind. That precedent is hard to ignore. But there is a case for the defense, and it deserves its say. Planets are not passive. A world with a molten, churning core generates a magnetic field, an invisible umbrella that deflects charged particles around the planet instead of letting them chew the sky. Earth holds its air partly because of that umbrella. Proxima b, if it is rocky and alive inside, could hold one too. Atmospheres can also be refilled. Volcanoes exhale. Comets deliver. A planet that starts with deep oceans has a vast reservoir to spend. Losing air is a race between erosion and replenishment, and we do not know which side is winning there. And red dwarfs calm down. Their stormy youth lasts long, but it fades. An older Proxima flares less than a young one did. The question becomes whether the atmosphere survived the star's furious first billion years, or grew back afterward, in the long calm that follows. There is one more twist worth holding because it complicates even the hopeful picture. A tidally locked world does not just risk losing its air to flares, it risks its air freezing out on the night side. On a planet with one face in eternal darkness, the coldest hemisphere can act like a trap. Gases drift there, chill, and settle as frost or snow that never melts, slowly pulling the atmosphere out of the sky and locking it to the ground as ice. Whether that happens is a race between the freezing and the winds. If the air is thick enough and the winds strong enough, heat and gas keep circulating faster than the night side can freeze them out, and the atmosphere survives whole. If not, the planet slowly undresses itself, one cold night that never ends. Climate modelers have watched both outcomes emerge from their simulations, depending on how much air the world starts with and how fast it spins. It is another fork in the road where we simply do not yet know which branch Proxima b took. And layered under all of it is the deepest uncertainty of all. We do not even know for certain that Proxima b is a rock. Its minimum mass says rocky. Its true mass could be somewhat higher, and a heavier version might hold a thick shroud of gas, or a deep envelope of water hundreds of kilometers deep, a world with no surface to stand on at all, just ocean fading down into exotic high-pressure ice. Temperate does not mean familiar. The habitable zone is a promise about temperature, and nothing else. So which is it? An ocean world under a red lamp, with black-leaved shores along a ring of eternal sunset? A frozen-out husk with its air snowed onto the night side? A steam-wrapped water world with no shore at all? Or a stripped stone, sterilized sometime in the deep past? Here is the honest answer, the one I owe you. Nobody knows. Not yet. Both remain on the table, defended by serious people with serious models. What I can tell you is that this is not a permanent ignorance. It is the kind with an expiry date. We already know the argument can be settled, because it is being settled right now for Proxima's cousins. 40 light-years away there is a famous system called TRAPPIST-1, an even smaller red dwarf, carrying 7 rocky worlds, several in its temperate band. Those planets happen to cross the face of their star from our vantage point, which makes them easier to examine, and the Webb telescope has been examining them, world by world, since it opened its eye. The first verdicts have been sobering. The innermost TRAPPIST worlds, so far, look bare, little or no air found. But those are the closest in, most flare-scoured of the 7. The jury is still out on the temperate ones. Every measurement there sharpens the same question we are asking about Proxima b. The red dwarf worlds of the galaxy are being cross-examined as a family, and the nearest member will not be exempt for long. Proxima b itself does not cross the face of its star from our point of view, we checked. That easy shortcut is closed. So its air must be read the hard way, by teasing the planet's own faint heat out of the star's glare. The hard way is not hopeless. It has a beautiful trick of its own. As the planet swings around its 11-day orbit, we see slightly different mixes of its day face and night face. If it has no air, the difference between scorching day and frozen night is huge, and the planet's combined heat should pulse strongly. If winds are spreading the warmth around, the pulse flattens. In other words, measure the heartbeat of its heat, and you can diagnose an atmosphere without ever seeing the planet as more than a single trembling point. Astronomy at its most detective-like, reading a world's lungs from its pulse. The tools for that are almost here. The Webb telescope has already begun studying other red dwarf worlds this way. And on a Chilean mountaintop, an instrument is rising this decade with a mirror 39 meters wide, the largest eye our species has ever built, with Proxima b written into its target lists from the start. Within years, not lifetimes, someone will publish the temperature map of the nearest temperate world, and we will know whether the nearest world breathes. Think of that as you drift. The question, is there air on the shore of the next star? Has an answer. It exists. It is simply on its way to us. Some nights I think the not knowing is its own kind of gift. We get to live in the last little stretch of history where the world next door can still be anything. Sleep on that one. When we wake, we will visit the 2 bright suns next door, and a ghost that the Webb telescope may have glimpsed beside one of them. We have spent our time so far with the small red star and its family, but most of the light at that address comes from the other 2, the bright pair, the 2 suns that sailors steered by, Alpha Centauri A and B. And the question everyone really wants answered lives there. A is practically a twin of our sun. B is close. If a temperate, Earth-sized world circled either one, it would be the most Earth-like setting we know of. A familiar kind of daylight, a familiar kind of year, 4 light-years from home. So, is there anything there? Before the planets, a small historical bow is owed to this pair. Because Alpha Centauri has been humbling astronomers since the very beginning of measured distance. In the 1830s, nobody knew how far away any star was. Not one. The method existed on paper. Watch a star from opposite ends of Earth's orbit, catch the tiny apparent shift, do the triangle. But the shifts were so small that a century of attempts had failed. A Scottish astronomer named Thomas Henderson, stationed at an observatory at the Cape of Good Hope, spent 1832 and 1833 measuring Alpha Centauri's position, over and over. When he worked through the numbers back home, the shift was there. The star was close, closer than any other measured since. But he hesitated to publish. The claim felt too large. He wanted certainty. While he checked and rechecked, a German rival announced the distance to a different star and took the honor of being first forever. Henderson published months later, the second stellar distance in history, and still the nearest. I keep his story in this night deliberately. Everything about Alpha Centauri, from the very first measurement to the planet candidates we are about to meet, has been like this. Enormous prizes, tiny signals, and the constant question of when you trust your own data enough to speak. The bright pair also gives us, in passing, one of the great unbuilt postcards of astronomy. From a world circling one of these suns, the other would swing between blazing beacon and small, brilliant lamp across each 80-year cycle. Some years casting real second shadows, some years just the brightest star in a foreign sky. Double sunsets, orange and gold, when the geometry allows. We have all seen that image in the movies. The nearest place the universe actually built it is here. This is the part of the story where science shows its human face. Because the search for planets around the bright pair has been a comedy of hope, heartbreak, and ghosts. I mean that kindly. It is what the frontier actually looks like. Begin with the heartbreak. In October 2012, a European team announced something extraordinary. A planet around Alpha Centauri b, Earth-sized. Circling its star in barely more than 3 days, far too close to be comfortable, a lava world, but a planet, at the nearest bright star. The news went around the planet in an evening. The signal was right at the edge of what instruments could do, a sway of about 0.5 meter per second. Slower than a stroll, slower than a tortoise. A star, nudged at tortoise pace, read from 4 light-years away. Other astronomers did what good astronomers do. They checked. And in 2015, a careful reanalysis showed the planet was never there. The signal was a ghost, an artifact born of the rhythm of the observations themselves, the gaps and cadence of the nights on the telescope masquerading as a world. The team that made the claim took it with grace. The team that unmade it took no joy. That is the method working exactly as designed. But it stung, and everyone in the field remembers the sting. Alpha Centauri BB is gone. You will still find it in older articles, a little tombstone of caution. Why is this so hard? 2 reasons, and they are almost funny. First, the stars are too bright. The dimness of Proxima is what made its planet catchable. A small star sways more, and its quiet light is easier to read precisely. The bright pair blazes. Their surfaces boil and shimmer, and that stellar weather drowns the whisper of any small world. Second, they are 2. Each star's gravity stirs the other's neighborhood. There are stable zones. Worlds could hold orbits close to either sun, out to roughly the distance of our asteroid belt. But the double glare and the double pull make every measurement messier. So for years the answer stood at no planets confirmed around the bright pair. Not no planets, no confirmations. An open door with nobody visible in the doorway. Then the ghost story got a sequel, a stranger one, and this time the ghost may be real. In 2019, an experiment on a giant telescope in Chile spent 100 hours staring at the pair in infrared, heat vision, trying to directly glimpse the warmth of any large planet. In the data, one faint smudge of heat beside Alpha Centauri A. provocative, unrepeatable, filed away as a maybe. And then came the Webb telescope. In August 2024, Webb turned its infrared eye on Alpha Centauri A, blocking the star's glare with a small mask. Beside the star, in the darkness where the glare had been erased, sat a faint point of warmth. Roughly where a giant planet would sit if it orbited about twice as far from A as the Earth sits from the Sun. A gas giant, by its heat, something in the neighborhood of Saturn's class, orbiting a sun-like star, in or near its temperate zone, 4 light-years away. If it is real, it is a landmark, the closest planet ever photographed around a star like ours. But listen to how carefully I had to say that. If it is real. Because when astronomers looked again some months later, the point of warmth was gone. Not necessarily because it was never there. A planet on a years-long orbit moves. The modeling shows an orbit that could carry it into the star's glare exactly when the follow-up looked. The earlier ground-based smudge from 2019 even fits some of the same orbits. The pieces allow a planet. They do not yet require one. So the status, honestly stated, is this: a candidate. Seen, lost, and lawyered over. The nearest sun-like star may have shown us a giant world in one photograph and then slipped it back into its pocket. The universe, it turns out, enjoys a cliffhanger. I should add what a confirmed giant there would mean. In our own system, Jupiter was a sculptor. Its gravity herded the asteroids, flung comets, shaped everything smaller than itself. A Saturn-class world in the warm zone of Alpha Centauri A would redraw every guess about what smaller worlds could orbit nearby. Perhaps clearing them out. Perhaps shepherding moons, large moons, temperate moons. A moon with oceans, circling a giant planet, under a sun like ours, next door. That is not a claim. That is a legally permitted daydream, and I offer it as one. Meanwhile, the hunt for smaller worlds around the pair continues with new tricks. One of my favorites is a small space telescope being built for exactly one job: to stare at Alpha Centauri and measure, over years, whether the two bright stars wobble across the sky by a hair's width. Not the color shift trick, but actual sideways motion, the tug of unseen companions written in position rather than pitch. The instrument's mirror carries a deliberately strange, flower-like pattern, designed to smear the starlight into a shape that reveals the tiniest displacement. A purpose-built eye for one address. And it is worth saying plainly why a small, rocky world around A or B would still be hiding, even if it is there. The color shift method that caught Proxima B needs precision at the level of a slow walk. An Earth in the temperate zone of Alpha Centauri A tugs its big bright sun at something closer to 1/10 of that, centimeters per second, a drifting off to sleep pace, while the star's own boiling surface shouts 100 times louder. The signal is not absent, it is underneath, buried in stellar noise the way a heartbeat is buried in a storm. Instrument builders are chasing that heartbeat with a doggedness I find genuinely moving. Spectrographs stabilized beyond anything pale red dot had, calibrated with laser combs, aiming for exactly that centimeter regime. Nobody has reached it cleanly yet. The first confirmed Earth mass world around a sun-like star, weighed by its sway, is one of the great pending achievements of this science. And there is a decent chance it happens at this system, simply because the nearest bright suns are where the trying is fiercest. That is where the bright pair stands tonight. One retracted world, one unconfirmed giant, photographed perhaps once, stable zones where small planets could hide below our current hearing, and instruments closing in year by year. There is a deeper reason the bright pair matters so much, beyond mere proximity. If a temperate, rocky world were ever confirmed around Alpha Centauri A or B, it would be, by a wide margin, the most Earth-like setting within reach. Not a red-lit, flare-scoured world around an ember, but a planet under a genuine yellow sun, with real days, real seasons, ordinary daylight. Everything that makes Proxima b exotic and difficult would simply fall away. It would be the closest thing to a second Earth the galaxy has yet offered us, and it would be next door. That is the prize that keeps the instruments trained on those two stars despite every difficulty. Not because the bright pair is easier, it is far harder, but because the payoff would be a world we could imagine standing on without a single caveat about red light or eternal afternoon. A familiar sky, 4 light-years away. And there is a poignant asymmetry here. Around dim little Proxima, we have found worlds, but they are strange. Around the sun-like star next to it, a familiar world would be a triumph. But it is exactly the kind of world hardest to detect, because a small planet around a bright star hides best of all. The universe, with a certain dark humor, has placed the most wonderful possible discovery in the one spot that is hardest to look. Compare the two doors of this system, because the contrast is beautiful. The dim red door, Proxima, is open. Worlds found, weighed, scheduled for atmospheric inspection. The bright golden door is still ajar, creaking, showing us shapes we cannot yet confirm. The nearest star system in the sky is keeping secrets from us in real time. Not out at the edge of the observable universe, here, 4¼ light-years away, across the street. I find that more comforting than frustrating somehow. It means the age of discovery did not end before we got here. The maps of the nearest shore are still being drawn, tonight, while you fall asleep. And now we know what is waiting. Worlds certain, worlds suspected, worlds still hiding. So we can finally turn to the question this whole night has been circling, the road itself. How does anything made by human hands cross 4 light-years of nothing? The first honest answer involves the rockets we actually have. And I will warn you now. The arithmetic is going to be humbling, and then, strangely, freeing. But that is for the next stretch of road. Rest here a while first. Now, the road. We know where it leads. A family of worlds around a red ember, and a possible giant hiding in the gold light next door. 4¼ light-years. Let us talk about actually going. Tonight we start with the vehicles humanity already owns. Chemical rockets. The kind that took us to the moon and threw the Voyagers out of the solar system. Because before dreaming of exotic engines, you should know precisely why the ordinary ones cannot do this. The reasons are not bureaucratic, they are mathematical, and they are beautiful in a merciless way. Here is the heart of it. A rocket is a machine that throws part of itself backward to move forward. Fire streams out of the nozzle. The ship recoils ahead. Simple. But every kilogram of that fire, the propellant, had to be carried until the moment it was burned. Which means the rocket spends most of its strength hauling the fuel it has not used yet. Fuel to push the ship. More fuel to push that fuel. More fuel again to push that. The requirement does not add up politely. It multiplies. It compounds like a debt. A Russian schoolteacher named Konstantin Tsiolkovsky wrote this into an equation back in 1903, before any real rocket existed. One short line of mathematics, and it has governed every launch in history since. The equation says, your final speed depends on how fast your exhaust leaves the nozzle, and on how much of your ship at liftoff is fuel. And the dependence is exponential. That word, exponential, is where interstellar dreams go to be humbled. The very best chemical exhaust streams out at about 4.5 kilometers per second. That number is set by the energy stored in molecular bonds. Chemistry itself caps it. No cleverness, no engineering, no budget raises it much. With exhaust like that, reaching Voyager-class speed, 17 kilometers a second, already demands a rocket that is overwhelmingly fuel, burned in stages that are thrown away as they empty. That is why launch vehicles are skyscraper-sized to deliver something the size of a car. Staging, by the way, is itself a confession. We shed the empty tanks as we climb because the equation punishes us for lifting even their dead weight, a rocket eating itself as it goes, leaving a trail of its own bones down the sky. It is the cleverest trick chemistry ever learned, and it buys us, at best, a few extra kilometers per second. The other trick we lean on is borrowing. The Voyagers got their speed less from their engines than from theft, swinging close behind Jupiter and Saturn and stealing a sliver of each giant's orbital motion. The planet slows by an amount no instrument could ever measure. The little probe leaves the encounter flung. Gravity assists are elegant, they are free, and they too have a ceiling. The planets only move so fast, and only lend so much. Everything chemistry and cunning can do together still lands us in that same bracket, tens of kilometers per second. The bracket of 70,000-year crossings. Now ask chemistry for real interstellar speed. Say, 1/10 the speed of light, 30,000 kilometers per second, the sort of pace that turns the crossing into a mere 40-something years. The equation answers with a mass ratio. For every ton of ship, the fuel required is a number so large it has no name. A 1 followed by thousands of zeros. Tons. Let me put that in perspective, although perspective is barely possible. The entire observable universe, every star of every galaxy, all of it, does not contain that much matter. Not close. Not within a rounding error of a rounding error. Chemistry does not say interstellar flight is expensive. Chemistry says no. Softly, completely, forever. I actually find the cleanness of that refusal calming. There is no near miss to agonize over, no almost. The door is simply not there. Whatever crosses to Alpha Centauri will not be a bigger version of anything on a launch pad today. It will have to be a different kind of thing entirely. So what is the fastest we have ever actually gone? The fastest launch from Earth was a small piano-sized probe called New Horizons, the one that photographed Pluto's heart. It left Earth at about 16 kilometers per second. At that pace, the crossing takes on the order of 80,000 years. The Voyagers, our farthest travelers, cruise at a similar order. I gave them their own night here, and their number was 75,000 years. And the fastest human-made object of all is the Parker Solar Probe, which has swung past the Sun at nearly 200 kilometers per second. A stunning number, until you notice it is borrowed. Parker is falling around the Sun, diving deep into its gravity and taking speed on loan. The Sun's pull reclaims the loan on the way back out, every orbit, with interest. That speed can never be pointed at the stars and kept. And I should be fair to the ordinary rocket, because it has one more trick that genuinely helps, just not enough. Beyond the giant's gravity slings, engineers have designed slower but steadier engines, ion drives, which do not burn fuel in a roar but breathe it out as a wisp of electrically charged gas, a bluish thread of thrust you could barely feel on your hand. Their exhaust leaves 10 times faster than any chemical flame, so they sip propellant and can run for years. Spacecraft using them have already reshaped their orbits across the solar system, quietly, patiently. But an ion drive trades brute force for endurance. Its push is feather light, building speed over months and years rather than minutes. It is a magnificent way to cross the solar system. Point it at Alpha Centauri, and the same arithmetic returns, only gentler, still tens of thousands of years, because even 10 times chemistry's exhaust speed is thousands of times too slow for the gap. The ion drive is the best rocket we actually fly. It still cannot make this trip in anything a civilization would recognize as a schedule. Even if it could, even at 200 kilometers per second, straight down the road, the trip to Proxima runs 6,000 or 7,000 years. 6,000 years ago, nobody on Earth had yet written a word. The whole history of writing, every letter and library, fits inside one-way ticket. And that is our speed record, borrowed and unkeepable. Notice the shape of the problem now. It is not distance alone. It is the marriage of distance and patience. We can build machines that survive the trip. The Voyagers will coast for millions of years, perfectly intact, needing nothing. Matter is patient. It is meaning that decays. The missions, the languages, the institutions, the people waiting for the answer. A probe that arrives in 80,000 years arrives to a species that has forgotten it, or outgrown it, or is not there at all. Consider what our longest completed projects actually are. The great cathedrals, begun by masons who knew their grandchildren might see the roof, some took 2 centuries, and we tell their story as a marvel of patience. The seed vault, dug into an Arctic mountainside, is designed, hopefully, for 10,000 years, and it mostly asks its future to do nothing but leave it cold. The oldest institutions still running, temples, universities, a handful of companies, are 1,000 or 2,000 years old, and they are freaks of survival, statistical wonders. Nothing human has ever run a project for 80,000 years. Nothing human has run one for 1/10 of that. When we price an interstellar crossing in millennia, we are not exceeding our engineering. We are exceeding our species' demonstrated attention span by a factor of 40. So the problem statement sharpens into something almost elegant. It is not enough to survive the road. You must cross it within the attention span of a civilization, which sets the bar with brutal clarity. To cross within a human lifetime, or even a project's lifetime, you need speeds counted not in kilometers per second, but in fractions of the speed of light. 1/10, 1/5, thousands of times faster than anything we have flown. And chemistry has already declined the invitation. Let me put the fuel problem one more way, because it is the whole reason the rest of tonight exists, and I want it to land in the body, not just the head. Picture trying to drive a car to a destination so far that you must carry all your fuel for the entire trip from the very start. No filling stations, ever. Now suppose the fuel is so weak that reaching your speed means the tank must hold 100 times the weight of the car. Fine, build a bigger tank. But the bigger tank is now the heaviest thing in the car, so it needs its own fuel to move, which needs a bigger tank still, which needs more fuel again. Each fix makes the problem worse than it solved. The car you actually need to go interstellar on chemistry is heavier than a planet, carrying a driver the size of a coin. That is not an engineering shortfall to be closed with a better tank or a cleverer nozzle. It is the exponential closing the road from the inside. And once you truly feel it, every exotic idea that follows tonight stops sounding like science fiction and starts sounding like simple arithmetic. The only kinds of engine whose numbers do not run away to infinity. Where else can the energy come from? Strip the question to its physics, and only a few doors exist at all. The energy locked in atomic nuclei, 1,000,000 times denser than chemistry's. The perfect annihilation of matter with antimatter, the densest energy there is, or the strangest door of the 3, carrying no fuel at all and letting the push come from somewhere else. Every serious interstellar design in history walks through one of those 3 doors. There are no others. Physics is a house with very few exits. In the next stretch of our night, we will walk through the first door, the nuclear one. It leads to some of the most audacious machines ever designed on paper. A ship meant to ride nuclear explosions, drawn up in deadly earnest in 1958 by people who had every intention of building it, and its gentler descendant, a fusion starship designed down to the rivets by a society of British engineers in the 1970s. Real blueprints, real physics, ships that could in principle have flown, and the very human reasons they never did. For now, let the exponential rest. It has done its work for tonight. The ordinary road is closed, formally and forever, and there is a strange peace in a door that shuts completely. The extraordinary roads are still open. We will walk them tomorrow, which is to say, in a few minutes if you are still with me. And it is perfectly fine if you are not. The stars keep. That is the one thing they are best at. The chemical road is closed. So tonight we walk through the first of the remaining doors, the nuclear one. And I want to tell you about 2 ships. Neither was ever built. Both were designed by serious people, with slide rules and budgets and test flights, in deadly earnest. The first one was meant to ride bombs. In 1958, in San Diego, a group of physicists began work on a project called Orion. The idea sounds like a joke until you sit with the numbers, and then it stops being funny and becomes slightly magnificent. A chemical rocket is limited by its exhaust, 4.5 kilometers per second, we said, but a nuclear explosion hurls debris at hundreds, even thousands of kilometers per second, millions of times more energy per kilogram than any fuel tank of chemistry. So, build a ship like a skyscraper standing on a vast steel plate. Drop a small atomic charge out the back. Let it detonate behind the plate. Ride the push. Then drop another, and another. A machine that sails on a chain of controlled apocalypses, one shove at a time. The plate takes the blast. Giant shock absorbers, pistons the size of grain silos, smooth the kicks into something a crew could survive. The designers called the charges pulse units. Bureaucracy can domesticate anything. Here is what separates Orion from fantasy. The physics checked out, and pieces of it were tested. In 1959, the team flew a meter-wide model on a stairway of ordinary chemical explosive charges. Bang, 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 and it rose, stable, and came down by parachute. The film survives. The thing flew. The men who worked on it, among them the physicist Freeman Dyson, one of the great minds of his century, genuinely expected to go. Their unofficial motto was Mars by 1965, Saturn by 1970. Crews of dozens, ships of thousands of tons. They meant it. And Dyson ran the numbers further out. Scale the ship up, refine the charges, accept a voyage of generations, and an Orion could, in principle, push toward a few % of the speed of light. Alpha Centauri, on the order of a century or two. Not comfortable, not fast, but finite. Achievable with 1960s physics, the first road in this entire story that actually reaches the destination within remembering distance. Dyson later wrote about those San Diego years with an ache you can feel through the technical prose. The team's plans grew almost drunk on possibility. Ships with barber shops and libraries, 100 colonists to Saturn, ferry service across the solar system by the 1970s. They budgeted the radiation, the fallout of the ground launches, and argued about it among themselves. The era was less careful than ours, and even then, the launch problem gnawed at them. The obvious fix was to assemble and depart from orbit, keeping the fire away from the sky people breathe under. I want you to hold the strangeness of the timing. This was before Apollo. Men with slide rules, a year after the first satellite, seriously designing vessels of 10,000 tons to ride atomic fire to the moons of Saturn. And the mathematics let them. That is the thing about Orion that never stops being uncomfortable. It was not ahead of its physics. It was ahead of everything else. Orion died in 1963, and it is worth being precise about the cause of death. Not physics. A treaty. The nations of the Earth, quite reasonably, banned nuclear detonations in space and the atmosphere. The ban made the world safer, and it made Orion illegal. Both things are true at once. The project folded quietly. Dyson himself wrote its obituary and mourned it for the rest of his life, while agreeing, mostly, with the treaty. There is something very human in that file drawer. The one propulsion system proven capable of the stars with the physics of its day, set aside on purpose, for good reasons, by the same species that dreamed it up. The second ship was gentler, and even more ambitious. In 1973, members of the British Interplanetary Society, an old, scrappy, gloriously unofficial club of engineers that had been sketching moonships since the 1930s, sat down to answer a simple question. With physics as we know it, no magic, could you design a real starship? Nuts, bolts, tanks, timelines? They worked on it for 5 years, in evenings and weekends. The result was called Daedalus, and it remains one of the most detailed starship designs ever produced. Daedalus swapped bombs for something tidier. Fusion, the joining of light atoms, the same fire that powers the stars. In its engine bell, tiny frozen pellets of fusion fuel would be dropped, 250 every second, and ignited by beams of electrons. Each pellet a miniature star, alive for a flicker. 250,000 heartbeats of starfire every second, for years. The design was enormous, some 54,000 tons at departure, most of it fuel, assembled in orbit. Its target was Barnard's star, 6 light-years out. The flight plan said half a century, cruising at around 12% of the speed of light. And because the ship could not stop, carrying fuel to brake would have doubled the impossibility. Daedalus was designed to do all its science in a screaming flyby, hours long, after 50 years of silence. Its builders accepted that. You take the century, you take the hours, you say thank you. One detail I love, the fuel. The best pellets wanted an isotope called helium-3, vanishingly rare on Earth. The Society's answer, straight-faced: harvest it from the atmosphere of Jupiter, with floating robotic refineries. Step 1 of the Starship: industrialize a gas giant. That is not a flaw in the plan. That is the plan being honest about the size of the ambition. Interstellar flight is not one machine. It is a civilization deciding to be the kind of civilization that does such things. Daedalus had descendants of its own, by the way. 30 years on, a new generation of volunteer engineers reopened the drawings. A successor study called Icarus, dedicated, in their own words, to the memory of the older project, asking what half a century of progress in computing, materials, and fusion research would change. The answer was, much of the detail, none of the verdict. A fusion starship remains buildable in principle, unbuildable in practice, waiting on a civilization that can light its fires. And the flame is closer than it was. The great fusion projects of our era, the tokamak rising in the south of France, the laser facility that finally coaxed a burning pellet past break-even, are crawling toward the day when fusion boils water for cities. Every step of that ordinary, unglamorous work is also, silently, starship research. The utility engineers do not think of themselves as building Daedalus's engine. They are anyway. Now, the sober footnote to both ships. Orion's physics worked, but the treaty stands, and should. Daedalus's physics mostly works on paper, but half a century on, humanity still cannot keep a fusion fire burning steadily even in a power station on the ground. We have lately, for the first time, made fusion fuel give back a little more energy than the beams that lit it. One flash, in one laboratory, a genuine milestone. But a starship burning 250 pellets a second for years remains far, far over the horizon. And I want to linger a moment on why fusion, specifically, is the fuel that will not lie down. It is the star maker, the reaction that lights every sun in tonight's sky, including the 3 we are traveling toward. A single gram of the right fusion fuel holds the energy of many tons of the best chemical explosive. Nature runs entire stars on it for billions of years, from nothing more exotic than hydrogen. The universe has proven the fuel works at industrial scale. It does so overhead every day. Our difficulty is not the fuel, it is the containment. A star fuses hydrogen by crushing it under the weight of an entire star. Gravity does the holding. We have no such weight to spare, so we must pin the fire some other way. Inside a cage of magnetic fields, or by crushing a fuel pellet with converging beams for the sliver of an instant before it flies apart. Both are like trying to hold a piece of the sun in a bottle we built ourselves. We are getting closer, decade by decade. The recent break-even flash in a laser lab was a genuine turning of the corner. But a starship needs that fire not for an instant, but sustained, controlled, and throttled, for years without a stumble. Between the laboratory spark and Daedalus's engine lies not a law of physics, but a mountain of engineering, and we are still on the lower slopes. And beyond fusion sits the last and richest fuel of all, antimatter. Perfect annihilation, matter meeting its mirror, both vanishing entirely into energy. the densest power source physics permits. Every gram outperforms fusion many times over. Science fiction runs on the stuff for good reason. The difficulty is almost comedic. All of humanity's laboratories together, running flat out, produce antimatter in billionths of grams per year, at a cost, per gram, that makes it comfortably the most expensive substance ever made. And it cannot be kept in a tank, because it erases any tank it touches. We suspend our few hundred atoms of it in magnetic cradles, briefly, delicately, like holding a snowflake over a furnace. A starship would want grams, kilograms. At present rates, the fuel run alone takes longer than recorded history. There is one more nuclear idea worth a moment, because it dodges the fuel problem from a completely different angle: the interstellar ramjet. The notion, dreamed up by the physicist Robert Bussard in 1960, is almost too elegant. Do not carry your fuel at all. Scoop it from space as you go. The gaps between the stars are not perfectly empty. There is a thin haze of hydrogen out there, a few atoms per cubic centimeter. Spread a vast magnetic funnel across hundreds or thousands of kilometers. Sweep up that hydrogen as you fly, fuse it, and throw it out the back. A starship that fuels itself from the void, that could in principle accelerate forever, closing on the speed of light with no tank to carry. It captivated a generation. And then the arithmetic caught up with it, as arithmetic does. The interstellar gas is so thin that the scoop must be monstrous. And worse, later analysis suggested that sweeping up that hydrogen and squeezing it enough to fuse it costs more drag than the fusion gives back in thrust. The scoop, some argued, works better as a brake than as an engine. The ramjet has been quietly reclassified over the decades from starship to beautiful mistake, though a useful one, since a magnetic scoop might still serve to slow a ship down at the far end, which, as we will see, is a problem nobody has truly solved. I keep it in the story because it is honest about how the frontier actually moves. Most bold ideas are not proven right. They are proven interesting and wrong in a way that teaches the next idea where not to step. So stand back and look at the nuclear door honestly. Behind it, real ships, real tests, real blueprints, machines that violate no law of physics and could, scaled and funded and permitted, cross to the stars in a long human timescale. What stops them is not nature. It is that they each demand a species more organized, more patient, and more united than the one that designed them. So far. The blueprints do not expire, though. Paper is patient, too. They sit in their archives like seeds in a drawer, waiting for a spring with different weather. And yet, while the great engines wait, a third door has opened, the strangest one. A road for ships that carry no fuel at all, weigh less than a coin, and are pushed across the void by light itself. Not a thought experiment, a funded program, announced in 2016, with hardware in laboratories right now. That door, the sail, is next. Rest a while first. The pellets can wait. They have kept for 50 years already. Every ship we have talked about tonight drowned in the same problem: the fuel. Carrying the energy for the trip means carrying mass. Carrying mass means needing more energy. The spiral eats every design. Chemistry drowned instantly. The nuclear giants drowned slowly in scale and politics. So in the end, the most serious plan humanity currently has for reaching Alpha Centauri does something almost insolent in its simplicity. It leaves the engine at home. Think about a sailboat. The boat does not carry its wind. The wind lives elsewhere, and the boat merely holds up a surface for it to press against. Now replace the wind with light. Light presses. This is real, measured physics. Every photon that bounces off a surface gives it a nudge. Sunlight is pressing on your window right now, with a force so tiny that a whole sunlit square kilometer collects only about the weight of a bag of sugar. Hopelessly gentle, you would think. But the gentleness comes with two loopholes. The push never runs out, and it arrives without a fuel tank. Small spacecraft have already sailed on sunlight alone. In 2010, a Japanese craft called Icaros unfurled a square kite of aluminized film, 14 meters on a side, and rode sunlight past Venus, the first true solar sail voyage in history. A decade later, a crowd-funded craft the size of a loaf of bread raised its own little sail in Earth orbit and, week by week, measurably climbed on light alone. No propellant, no engine, pressure of photons, doing real navigation. That technology exists. It has flown. Ordinary people paid for some of it. But sunlight weakens with distance. It can trim an orbit, not hurl a ship at the stars. So concentrate the light. Replace the sun's soft glow with a beam. That is the whole idea behind Breakthrough Starshot, announced in April 2016, the same season, funnily enough, that Proxima's planet was being confirmed. A privately funded research program launched with $100 million, backed by physicists of the first rank, with one goal: work out how to send something to Alpha Centauri within a generation. Here is the shape of the plan, and I promise you every number is from their own working papers. First, shrink the ship. Not a vessel, not a probe in the classic sense, a chip, a few grams. A wafer the size of a postage stamp carrying cameras, sensors, a laser for calling home, and a scrap of computing. They call it a star chip. Mass production, thousands of them, because at a few grams each, you can afford to send a fleet and lose most of it. Second, give the chip a sail, a few meters across, thinner than soap film, lighter than a butterfly, made of materials chosen to reflect almost everything and absorb almost nothing. Absorption is death. A sail that swallows 1 part in 10,000 of a 100-gigawatt beam simply becomes vapor. Third, the engine that stays home. On a high, dry mountaintop, build an array of lasers spread over a square kilometer, their beams locked together into one. Combined power, on the order of 100 gigawatts. For scale, that is roughly the output of 100 large power stations, but needed only for minutes at a time. Aim the beam at the sail. Hold it there for a few minutes. In those few minutes, the little wafer accelerates at thousands of gravities and leaves the beam traveling at roughly 1/5 of the speed of light. 60,000 kilometers every second. From a standing start to 20% of light speed between one cup of coffee and the next. At that speed, the crossing to Alpha Centauri takes about 20 years. Add 4.25 more for the report to fly home at light speed. Total, a mission whose beginning and end fit inside one career, one adulthood, one human memory. Someone alive on launch day opens the pictures. That is the promise. Now the honesty, because the problems are ferocious. And this channel does not sell dreams without the price tag. Problem 1. The beam. 100 gigawatts of laser light, formed by thousands of individual emitters, must pass through Earth's rippling atmosphere and converge on a sail a few meters wide, thousands of kilometers up, holding steady to a precision that makes a sniper look casual. The atmosphere fights you. The technology to unripple it exists, but never at this scale. Problem 2. The sail must survive its own engine. Under that beam, it rides a pressure and temperature environment no thin film has ever endured. It must reflect nearly perfectly, stay balanced on the beam like a bead on a fountain, and not tear at accelerations that would flatten any machine we have ever flown. Problem 3. The void is not quite empty. At 1/5 of light speed, a dust grain is a cannon shell. Even single atoms of interstellar gas, met at 60,000 kilometers a second, slowly sandblast the leading edge. The studies suggest a chip can survive the crossing if it flies edge-on and accepts some scars. But the margin is thin, and this is one reason you send a fleet, not a flagship. Problem 4, and it is the poignant one. There are no brakes. None. The beam that threw you cannot slow you. There is nothing at the far end to catch you. The star chips cross the entire Alpha Centauri system, the system we have spent this whole night learning to love, in a matter of hours. 20 years of flight. A few hours of arrival. A handful of photographs of Proxima b snatched at 60,000 kilometers per second. Then the little wafer sails on into the dark forever, still calling home as long as its laser lasts. And those photographs would take 4 years and 3 months to crawl back to us. A transmission from a coin-sized ghost, fainter than faint, caught by the same giant dishes that today strain to hear the Voyagers. Even that call home is its own research program. A chip cannot carry a dish. Its voice is a tiny laser, and its power budget at Proxima might be less than a nightlight's. The plan leans on a lovely reversal. The same square-kilometer array that launched the fleet turns from cannon to ear, collecting the arriving photons a handful at a time. The picture of another world may come home literally photon by photon, assembled over months like a mosaic delivered one tile a week. And the program has already flown its first ancestors. In 2017, the team piggybacked a batch of centimeter-scale prototype spacecraft into orbit, complete satellites on single circuit boards, a few grams each, whispering home on milliwatts. Toys by Starship standards. But so was the first aeroplane. When people ask whether Starshot is realistic, I give the honest, two-part answer. No law of physics stands in its way. That is precisely what separates it from warp drives and wormholes. And yet nearly every component must be pushed far beyond the current state of the art. The lasers, the optics, the materials, the miniaturization. The program's own people talk in decades of research before any launch. This is a project on the scale of a generation, priced accordingly. But notice what has already happened, quietly, regardless of whether this particular sail ever flies. For the first time in history, the crossing to another star is an engineering problem, not a fantasy, not a metaphor. A list, a long, brutal, itemized list of solvable difficulties, each with laboratories working on it right now. Chemistry said never. The bombs said maybe, at a price no one would pay. The sail says 20 years, once the homework is done. It is worth naming the deepest catch of all, the one no cleverness removes, the light speed wall itself. 20% of light speed is astonishing, 1,000 times faster than any ship we fly, and it still means 20 years each way, plus the 4-year crawl of the news coming home. Push for half of light speed, and the engineering difficulties do not merely double, they climb toward the impossible, and the trip shortens only modestly. Nature has hung the destination just far enough that even our boldest realistic plan spends decades on the road. You do not beat the light speed wall. You negotiate with it, and it drives a very hard bargain. Which is why, even in the sail's best case, this remains a mission measured against a human life, not a human afternoon. A person who helps switch on the laser array as a young engineer might, if they are lucky and the homework went well, be elderly on the evening the first pictures of another world's shoreline finally trickle home. One career, bookending one crossing. That is the fastest, honest timeline our species has, and it is worth sitting with how long even the fast road is. And there is something fitting, I think, in how the answer turned out. We spent centuries imagining mighty ships, argosies with engines like cathedrals, and the first real plan looks nothing like that. It is a beam of light and a scrap of foil, small enough to lose in a drawer. There is a lineage to this idea worth honoring, too, because the sail did not spring from nowhere. The pressure of light was predicted in the 1800s by the physicist James Clerk Maxwell as a consequence of his equations for electricity and magnetism. Light, he showed, must push on whatever it touches. It was measured in a laboratory in the early 1900s, a fantastically delicate experiment weighing the weight of sunshine. The idea of sailing a spacecraft on it was written down by a Russian rocket pioneer, the same tradition that gave us the merciless fuel equation nearly a century ago. And the notion of pushing such a sail with a beam rather than the sun was worked out in detail by the physicist Robert Forward in the 1980s, who imagined enormous lenses and lasers hurling sails to the stars. So Starshot is not a break with the past. It is the moment a 100-year-old idea finally met the technologies it was waiting for. Lasers powerful enough, materials thin enough, computers small enough to ride a chip. Sometimes an idea is simply early and has to wait, patiently, for the century that can build it. The sail waited 4 generations. It may yet wait a 5th. But the waiting is the ordinary rhythm of these things, not a sign of failure. The universe rewards the humble approach. It usually does. Of course, a flyby of a few hours answers only the first questions. To orbit those worlds, to land, to stay. That calls for the heavy roads after all, or for passengers of a very different kind. Ships that carry not people but generations, or people but asleep. That is where we walk next, the slow road, and what it does to the travelers. It is the most human stretch of this whole journey, but not yet. For now, picture the little sail riding its thread of light out of the solar system, shining, silent, absurd, and brave. It weighs less than the change in your pocket. It is the fastest thing our species has ever seriously planned to make. Sleep well beside that thought. The sail crosses in 20 years, but it cannot stop, and it cannot carry us. So tonight we walk the other road, the slow one, the road for ships that do stop and do carry people. It is the oldest idea in this whole story, and the most human, and the most troubling once you sit with it honestly. The generation ship. The logic is disarmingly simple. If the crossing takes centuries and a human life is decades, then no traveler who departs can arrive. Fine, says the idea, send a village. Let the voyage be lived in, not survived. The ones who launch will die aboard. Their grandchildren's grandchildren will walk out under a red sun. You are not sending a crew. You are sending a people. The idea is older than spaceflight itself. In 1918, the rocket pioneer Robert Goddard, whose name is on a NASA center now, privately wrote out a scenario he called the ultimate migration. Humanity, in the far future, sending an ark away from a dying sun. He sealed the manuscript in an envelope marked, "To be read only by an optimist." In 1929, the physicist John Desmond Bernal imagined hollow spherical worlds, mid-ocean ships of space carrying tens of thousands of people between the stars. The generation ship was dreamed up before anyone had flown a liquid-fueled rocket over a fence. Engineers have sketched such ships ever since, vast rotating cylinders, kilometers long, spun for artificial gravity, with farms and forests and weather curled up along the inside of the hull. Sunlight from a fusion lamp down the axis, rain from condensation on schedule. A worldlet, sealed and thrown. The pictures are gorgeous. The physics of the hull and the spin is honestly fine. The hard problems live elsewhere, in the biology and in the passengers. Problem 1. The ship must be a working ecosystem, closed tight, for centuries. Nothing in, nothing out. Every atom of air, water, and food circling around and around, life to waste, to soil, to life. Without drift, without collapse, for longer than most nations have existed. We have tried a closed ecosystem exactly once at habitat scale, a famous glass ark in the Arizona desert, sealed in the early 1990s with 8 people inside, rainforest and ocean and farm under one roof. It lasted 2 years, and it fought them the whole way. The oxygen crept downward, month after month, for reasons nobody caught in time. The building's own concrete, it turned out, was quietly eating it. Crops underperformed. Pollinators died. The 8 split into factions that, by some accounts, were barely speaking by the end. None of that is failure to mock. It is data, the only data of its kind we have. And the data says, a sealed biosphere is not a machine you build. It is a balance you tend. And we do not yet know how to tend it for 2 years, let alone 200. Problem 2 is subtler. How many people does a village in a bottle need? Too few, and the gene pool narrows generation by generation until the colony fails in slow motion. Too many, and the ship balloons beyond building. Researchers have modeled it seriously, simulating births, deaths, accidents, inheritance, over centuries of simulated flight. One careful study of a 6,300-year voyage to Proxima put the minimum crew at just under 100 people, with a few hundred preferred for safety margin. 100 people. The population of one small apartment building, carrying the whole human story across the dark. Problem 3 is the one that keeps philosophers awake, and it has no engineering answer at all. The people of the middle generations never chose the voyage. They are born between stars, live between stars, and die between stars, farmers and teachers and mechanics of a corridor world, keeping the machine alive so that strangers, centuries downstream, can have a landfall the middle generations will never see. Is it right to sign your descendants up for that? The launch generation volunteers. Generation 5 did not. There is real philosophy written on this, in earnest. The ethics of consent stretched across centuries, and I will not pretend the question is settled. It is the kind of question a civilization should argue about for a long time before it builds such a ship. Perhaps that argument is itself part of the journey. And history offers one warning more, almost gently. Culture drifts. A society sealed in a can for 500 years will not arrive speaking the language that launched, or valuing what the builders valued. Some fiction imagines crews who forget, mid-voyage, that they are on a ship at all, the corridors becoming simply the world. It is fiction. But drift is not. Every isolated human community we have ever studied changed faster than its founders dreamed. Whoever steps out at Proxima will not be us. They will be who the road made them. So the generation ship is really a bet that a society can stay competent, sane, and kind for centuries in a corridor, unsupervised. Look at any 5 centuries of Earth history and judge the odds yourself. Which is why, for as long as the generation ship has been imagined, there has been a quieter counterproposal walking beside it. If the voyage is too long for a waking life, do not stay awake. Sleep. The travelers board, lie down, grow cold, and the centuries pass over them like one long anesthesia. The arithmetic collapses. No farms, no schools, no middle generations, no consent problem. The very people who chose the voyage are the ones who arrive, barely older than they left. Every spacefaring film you have ever watched leans on those glass sarcophagi. So let me tell you, plainly, where the science actually stands. Nothing like human hibernation exists. Nothing close. What exists is this. Hospitals routinely cool patients by a few degrees for hours. Therapeutic hypothermia, slowing the body's fires to protect the brain through cardiac arrest and surgery. It works, and it is the one solid stone in this whole river. Space agencies have funded studies of stretching that, cooling a crew into torpor for days or weeks on a Mars run, nutrients by vein, waking on rotation. Paper studies, medical reviews, cautious and real. No human has yet been put under for even 1 week, and the animals that do it for real, bears, ground squirrels, creatures that shut themselves down every winter, carry a genetic toolkit we are only beginning to read, and do their sleeping for months, not decades, warm-blooded miracles though they are. Between a cooled patient in an operating theater and a colonist sleeping for 2 centuries lies a canyon of unsolved biology, cells, memory, the slow chemistry of aging that does not fully pause. It may be crossable. Nothing forbids it. But tonight, in any honest accounting, the sleeping ship is a beautiful blank space on the map. There is a 3rd passenger manifest. Stranger still, send no adults at all. Send the seeds of them, frozen embryos, tended by machines, to be raised at arrival by artificial guardians. Frozen embryos are proven medicine. Healthy children have been born from embryos stored for 30 years. but raising them at the far end without a single human hand, that asks machines to be parents, and no machine has ever been anything of the kind. I mention it because serious people mention it, and I file it, clearly labeled, under speculation. There is a gentler cousin of the generation ship worth setting beside it, not a single vast ark, but a wandering world. Some thinkers have pointed out that humanity may not need to build a starship at all, if it learns first to live permanently on small, icy bodies, comets, dwarf worlds of the outer solar system, carrying their own water, their own shelter, their own buried warmth. Live that way for long enough, spread slowly outward through the sun's own cloud of distant comets, and the edges of that cloud eventually brush the edges of the next stars. You would not launch a ship to Alpha Centauri. You would simply keep living outward, generation by generation, until one day your descendants' comet home is closer to the new star than to the old one, and nobody aboard ever felt they left. It is migration without a voyage, the way life has always actually spread, not in single heroic leaps, but in a slow tide that never quite noticed it was moving. I find it the most plausible picture of all, precisely because it asks for no miracle engine, only time, and the patience to treat the dark between stars as somewhere to live, rather than somewhere to cross. That patience, of course, is the very thing we cannot yet prove we possess. Which brings us back to the hard truth under all of it. Step back now and see the slow road whole. The physics is the easy part. Even the nuclear engines we shelved 2 chapters ago could push a village ship to a few % of light speed. What the slow road really tests is not propulsion. It is us. Our ecology, our genetics, our politics, our patience, our right to choose for the unborn. A generation ship is a mirror with engines. And there is a quieter danger to the slow road that has nothing to do with machinery, and it is worth naming because it is the one nobody can engineer away. On a voyage of centuries, the reason for the voyage can simply fade. The people who launched had a purpose that burned bright enough to sign away their descendants' lives to it. But purpose is not inherited like eye color. Generation 10 might look around at the humming corridors, the recycled air, the star that has not visibly moved in their lifetime, and ask the question no crew wants asked. Why are we still doing this? What if they decide halfway that the corridor is enough, that they would rather turn the ship into a home that goes nowhere than a vessel forever aimed at a stranger's shore? Nothing forces them to complete the mission. There is no mission control to overrule them, no authority within 4 light years. A generation ship is, in the end, a small society that must re-choose its own purpose, freely, every single generation, for longer than any purpose in human history has ever survived. That is not a fuel problem or a life support problem. It is the deepest problem of all. Whether meaning itself can be kept alive across centuries in a sealed room. We have never tested it. We may not be able to. And maybe that is the real finding of this whole stretch of road. The distance to Alpha Centauri is measured in light years on the way out, and in maturity on the way in. We are not ready. That is not despair. That is a diagnosis with a treatment plan. Every year the ecosystems get better understood, the biology gets deeper read, the little sails get closer to flight. The species is doing its homework, unevenly, the way it always has. And while the homework continues, the destination waits with perfect patience. The red ember, the 11-day world, the 2 golden suns, keeping their secrets for whoever finally makes the crossing, in whatever form they take. Next, we allow ourselves the reward for all this honesty. We arrive. However it happens, whenever it happens, the next stretch of our night is landfall. What a visitor at Alpha Centauri would actually see, hear, and send home. But that is for after the rest. Sleep now, if you have not already. The village in the bottle sails on without us tonight, imaginary and patient, somewhere in the long dark between the maps. We have earned this part of the night. We have done the honest arithmetic, closed the false doors, price the real ones. So now, briefly, carefully, let us simply arrive. Imagine the crossing is behind us. However it was made, a fleet of gram-weight sails, a slow nuclear freighter, a village of the descendants of volunteers. The engines, whatever they were, are quiet now. Ahead, where every sky of every human generation has shown a single bright point, there are suns, plural, growing. The first thing an arriving traveler notices is the light. Two golden suns, still far apart in space but close in the sky. One like home, one smaller and amber, casting double shadows that open and close like scissors as the ship moves. Every rock in this system, every ice grain, has two shadows. It is the simplest, strangest signature of the place. Nothing here has ever had just one. Imagine standing on a world of the bright pair and watching a day end there. One sun sets, and the sky does not go dark, because the other is still up, or rising, painting the landscape in a second color, throwing your shadow the other way. Days without true nights, for stretches of the 80-year cycle. Then, when the two suns swing to the same side of the sky, ordinary darkness returns for a while. A calendar with two hands moving at different speeds, a rhythm of light no human culture ever had to name. Whoever lives there, if anyone ever does, will invent words we do not have, for skies we have never stood beneath. And over it all, if you knew where to look, one particular unremarkable yellow star, low on the horizon, brighter than most, but nothing special to an untrained eye. Home. The sun, seen from the far shore, reduced to a single point among the thousands. Everything that has ever happened to our entire species, every war and love and song, all of it under that one modest star that the locals, if there were locals, would never look at twice. And lo and away, dim and red, the third light. The ember, our first port. A visitor decelerating at Proxima, and we will grant our travelers breaks tonight. They have earned them too. Falls first past the outer candidate world, the cold, maybe planet, on its 5-year road, a dark globe with starlit ice if it is there at all. Then, inward, quickly, this system is tiny, remember, a clockwork squeezed 20 times tighter than ours, past the middle orbit, toward the world we came for. Proxima b, from orbit. I will not pretend to tell you what it looks like. Nobody alive knows. But the possibilities are few enough to hold in one hand, and we have met them all tonight. It might rise ahead as a marble of ocean and cloud, its permanent dayside sea glinting rose gold under the ember light, a ring of sunset fire standing forever around its rim, the eye of the world, open toward its star. Or it might come up airless and still, a beautiful corpse, craters sharp as the moon's, the temperate zone's promise spent long ago under the flares we spoke of. Either way, and this is the part I find quietly overwhelming, within hours the travelers know. Questions that hung over Earth's astronomers for generations, argued in journals, modeled in dissertations, dissolve one after another at a glance. Is there air? Are there seas? Is the night side frozen? The whole library of our careful guesswork, graded at last, in an afternoon. That is what arrival is, really. Not planting a flag, grading the homework of centuries. And after the glance, the slow feast. Orbiters mapping the eternal afternoon in every wavelength. Weather, alien weather, the first ever watched live, spiraling against the terminator, storms that have never once moved off their meridian. Radar sounding the night-side ice for buried oceans. The seismology of a world nobody has stood on, read from orbit by laser. Every instrument we ever perfected around Mars and Jupiter and Saturn, opening its eyes around another sun. If there is air and water, then somewhere in the second week, someone flies the first drone down through a red afternoon that has lasted 4 billion years, over whatever passes for a shore, and takes the photograph. the one that gets printed as large as walls for the rest of history. And if it is the other outcome, the bare stone, then honesty insists that too is a landfall. Geologists will read 4 billion years of that world's diary in its cliffs. The flares that stripped it wrote their history into its rocks. Even a dead Proxima b is the first page of comparative planetology around another star, the control experiment for every living world we ever find after. Science has no wasted arrivals. I sometimes think about the sound in the cabin in that moment. I suspect it is not cheering. I suspect it is the particular silence people fall into in cathedrals. There is one more piece of arrival, and it is the one that binds the whole story back to us, here, on the pillow side of the gap. The travelers cannot tell us what they found, not in any way that feels like telling. Every word they send crawls home at the speed of light, 4 years and 3 months in transit. Ask a question, and the answer returns in 8.5 years, best case, ever, no improvements possible. The speed of light is not a technology. It is the shape of the universe. So there is no mission control for Alpha Centauri. No guidance from home, no rescue, no reassurance. Whoever arrives is, by physics and not by policy, on their own. The most independent human beings, or human descendants, or human machines that have ever existed. And the communication that does flow becomes something older than conversation. Annual reports from another star. Letters, in the deepest sense, composed knowing the reader is years away, answered by someone who has already lived years past the asking. Humanity has done this before, actually. For most of history, an ocean crossing meant exactly this. A voyage of years, letters that outpaced nothing, families who followed a life in packets 18 months stale and were not broken by it. We know how to love slowly, across distance. It is in the repertoire. We would just be doing it astronomically. Think, too, about what the first deliberate message home would carry. Not just data, but meaning. When the Voyagers left, we bolted golden records to their hulls. Greetings in 55 languages, the sound of rain and a heartbeat and a mother's kiss. Music from across the earth, all sealed for a journey of tens of thousands of years toward stars nobody chose. That was a message sent outward with almost no hope of an answer. A letter dropped in an ocean the size of the galaxy. A signal from a probe at Alpha Centauri would be the mirror image of that gesture. Not us speaking blindly into the dark, but a piece of us that reached the far shore and turned to call back. The first radio whisper from the nearest star, however faint, however slow, would be the answer to the loneliest message we ever sent. It would mean the ocean has a far side, and we touched it, and something of ours is standing on it, waving. I do not know whether that call comes in 50 years or 500, but the shape of it is already set by physics, and it is a shape our species has known for a very long time. The letter that crosses the water, the light that left before you were ready, the answer that arrives to a changed world. Some of those letters, near the end of our own century perhaps, might be read by children who ask their parents which star the writing comes from, and be shown it, that bright southern point the sailors steered by, the point that answers now. Could the travelers stay, settle, make the red-lit world a home? Honesty to the end, every option is hard. If Proxima b lives, it is a world of one eternal afternoon, flare-lit, heavy-skied, nothing like a second Earth, a place you inhabit the way researchers inhabit Antarctica, purposefully, carefully, perhaps permanently, but never casually. If it is dead, the settlers live inside their own walls there as they did on the voyage, and the planet is a quarry and a view. Remaking such a world wholesale, terraforming, in the grand sense, sits far beyond any near horizon, a project for millennia if it is possible at all. I give you that not to close the door, but to size it truthfully. First shelters, yes, Gardens under glass in the ring of sunset, conceivably. New Earths, not soon, and perhaps not there. And maybe that is fine. Maybe the point of the first arrival was never real estate. Here is what will certainly be true. The evening the first report from Alpha Centauri reaches home, whether that evening comes in 50 years or 500. Somewhere on Earth, the news arrives as light in a dish, 4¼ years old. And from that evening onward, the human story has two addresses. Everything before divides from everything after. The species that told itself stories about the stars becomes, in the oldest sense of the word, correspondence. The gap does not close. The gap gets a bridge of letters. One journey remains for us tonight, the longest of all, and the gentlest. We step back from years and centuries and let the road itself change under deep time. Stars drifting, distances breathing, the map redrawing itself over ages. It is the finale, and it ends, I promise, somewhere very calm. Stay or sleep. The letters travel either way. And so we come to the last stretch of the night. We have walked the road to Alpha Centauri in every way a mind can walk it. For the finale, I want to lift us above the road entirely, because there is one traveler in this story we have not yet honored: time itself. Everything we said tonight assumed the map is fixed. Here is the sun. There is the ember. 4¼ light years of dark between, forever. But the stars do not hold still. Every star you can see is falling through the galaxy on its own long orbit, our sun included, all of us circling the distant hub of the Milky Way, once every 250 million years, each star on its own lane, at its own pace. The constellations you learned as a child are not architecture. They are traffic, photographed once. And the traffic is moving. The Centauri system is not merely near us, it is approaching. The gap we spent all night measuring is closing, on its own, by more than 20 kilometers every second, with nobody lifting a finger. Give it time. In roughly 27 or 28,000 years, Alpha Centauri makes its closest pass, around 3¼ light years out, nearly a full light year closer than tonight. A quarter shorter, the Great Road, simply for waiting. 28,000 years sounds like an absurd length of time to wait for a discount, but hold it against the other numbers we have carried tonight. It is close to the same span the cave painters of the last ice age stand from us, and their handprints survive. It is 1/3 of the Voyager crossing we priced at the start of the night. On the clock this story runs on, it is soon. And after the pass, the slow tide turns. Centauri sweeps by and begins to recede for ages upon ages, until 100,000 years from now, it is no longer the nearest star at all, and some other sun inherits the title, and some other night sky's watchers, if any are watching, get their own bright neighbor to wonder about. The title of nearest star is a relay baton. Proxima merely happens to be carrying it during the brief era when someone is here to notice. And this has all happened before. We have the receipts. Combing the star catalogs backward through time, astronomers found that about 70,000 years ago, while modern humans were already walking the Earth, a dim little red star with a dimmer companion actually brushed through the outer fringe of the sun's comet cloud, passing several times closer than Alpha Centauri is now. It is called Shortens' star, after its finder. Whoever looked up on those nights saw nothing. The visitor was too faint for eyes, but it was there. A foreign sun inside the fence, while our ancestors slept by their fires. Interstellar neighbors are not a hypothetical then. They are a recurring appointment. Deeper still, the traffic delivers. Astronomers tracking the catalog of nearby stars have found one, an unremarkable small orange star, a bit heavier than Proxima, whose lane runs almost straight at us. In about 1.3 million years, it is expected to pass through the outer edges of our own Oort cloud, the sun's halo of sleeping comets, some 25 times closer than Alpha Centauri stands tonight. For a stretch of a few tens of thousands of years, our descendants, if descendants there are, will have a star in their cometary suburbs. The interstellar crossing, the impossible gap we spent this whole night pricing, will briefly shrink to something almost neighborly. Deep time builds its own bridges. I love what this does to the story. It means the great crossing is not a fixed exam the universe set us. The exam itself drifts. Distances breathe in and out over the ages like a slow tide, and a patient species, a truly patient one, could simply wait for the ferry. And it reframes something we treat as permanent, the night sky itself. Every constellation you can name is a temporary arrangement, a chance alignment of stars at wildly different distances, each drifting on its own path, that happens to spell a shape from our vantage point during our particular eye blink of cosmic time. Wind the clock forward 100,000 years and the familiar patterns dissolve. The plow bends out of shape, the hunter's belt scatters, and new figures nobody has named assemble in their place. The sky our distant descendants inherit will not be ours. It will be as strange to them as an unmapped country. Somewhere in that redrawn sky, Alpha Centauri will have slid on past its closest approach and begun the long retreat, no longer the nearest star, its brief tenure as our neighbor finished. And some other sun will hold the title and be studied and perhaps be visited by whoever is keeping watch then. There is a strange comfort in that impermanence. It means we are not late to the story and we are not early. We are simply here, during one particular arrangement of the lanterns, with one particular star nearest to hand. The map we are drawing tonight is not the eternal map. It is our map, of our moment. And that is exactly what makes it worth drawing. Now bring all of it home, one last time, to the two machines where our story tonight really began. The Voyagers are out there this minute. I told you their story before this one, and the two stories are really halves of one. They carry their golden records, their frozen greetings, 70,000 years of coasting between them and the neighborhood of any star. On every scale that matters to a life, they are lost to the dark. On the scale this final chapter runs on, they have barely left the driveway. And the dark is not empty at all, but full of slow traffic, lanes crossing and closing, stars trading places like lanterns carried by walkers on a vast, unhurried plain. Somewhere in that traffic, our little machines drift with their letters, and somewhere ahead of them, always, is a nearest star. Let me leave you with one last change of scale, the gentlest of the night, because I think it is where all of this finally comes to rest. We have spent these hours treating 4 light years as an almost unbridgeable gulf, and for a body of flesh and metal, tonight it is. But widen the lens all the way out, to the size of the galaxy itself, and Alpha Centauri and the Sun are not far apart at all. They are 2 lights among 400 billion, sitting side by side in one quiet spiral arm, both circling the same distant center, both born from the same slow churning of the same galactic gas. On that map, they are neighbors in the truest sense, near-identical travelers on near-identical roads around the Milky Way, keeping a loose, ancient company that will last for ages yet. We did not choose this neighbor. The galaxy dealt it to us, the nearest door happening to hold a sun-like star, and an orange sibling, and a red ember with worlds. It could have been a barren white dwarf, or a violent young giant, or nothing reachable at all for hundreds of light years. Instead, the closest thing in the entire universe to us is a place with suns like ours and worlds in the temperate zone. Of all the ways the cards could have fallen, they fell kindly. So what do we actually hold at the end of the night? Let me stack it up gently, like putting books back on a shelf, one by one. The nearest star is real, and it is 3, and we have known it barely a century. It has worlds. That is settled forever now. A temperate one at least, 11 days to its year, a red lamp for a sun, and perhaps a hidden family around the golden pair next door, showing themselves one photograph at a time. The road there is closed to chemistry, open on paper to the atom, and open in earnest, 20 years, once the homework is done, to a scrap of foil on a thread of light. The travelers, when they go, will be letters more than voices, and the ones who stay behind will learn again what every harbor town once knew: how to love someone whose news comes by the year. And underneath it all, the map itself is alive, the distances breathing, the nearest star leaning slowly toward us as if the universe, in its own geological way, were meeting us halfway. None of tonight was science fiction. Every number came from a published page. Every open question was labeled as open. That is the strangest part, and the part I most wanted you to have. This is simply where we live now, between the first star and the second, early, impossibly early, in a story that has already verifiably begun. People sometimes say the age of exploration is over, that the maps are finished. The maps are not finished. The maps have barely started. 4 light-years away there is a shoreline no one has seen, with 3 suns over it, and the first hand-drawn charts of it are being corrected tonight, by quiet people at telescopes in a desert, while the rest of the hemisphere sleeps. You were awake, or half awake, for a little of the drawing. That is all any generation gets, and it is enough. Some night, years from now, walk somewhere dark enough for the southern sky and find the 2 bright points low over the horizon, the pointers, the sailors' stars, third brightest in all the night. You will know, now, what is actually there. The double gold, the hidden ember, the 11-day world, the ghost in the Webb photograph, the little sails on their drawing boards aimed straight at it all. The nearest star, the first rung, the whole ladder waiting above it. But that is for some other night. This one has done its work. The ember will hold its worlds till morning. The sails will keep in their laboratories. The letters, when they come, will be years in the post anyway. Nothing out there requires you awake. So let it all drift now. The suns, the sails, the slow, bright traffic of the stars. Rest easy. Sleep well. Good night.